This video is part 2 of a 2-part instructional video that covers real-world CAD slide routine. This video will explain in detail the use of the slide routine with graded pipe and plumbing systems, as well as options offered for angled pipe installations. While there will be some theoretical demonstrations in this video, our primary focus will be on real-world problems. In the first real-world example, we'll use the slide routine to place the waste and vent fittings on this simple lavatory header. Next, move to our warehouse project where we'll see how to use the slide routine to place nozzles on this fire protection system, which employs a sloped primary manifold. Then we'll switch to this rather complex toilet room header to see how we can use some of the various options the slide routine offers to place the fittings. Later we'll switch back to the warehouse project where we'll use the slide routine to place this Y to remain clear of this truss. Then we'll move to our parking structure project. Here we'll use the slide routine to place all of the fittings shown here. We'll even use one of the routine's options to clear the ramp beam above and provide maximum headroom. For our last real-world examples, we'll switch to our office project. Here we'll use the slide routine to place the pipe and fittings in this vertical offset. We'll see how to use it in conjunction with the angle Z routine to clear the ductwork below while maintaining the proper grade on the plumbing run. Finally, we'll use the slide routine to place the pipe and fittings for this rolling offset. First, we'll run the pipe around this column shown in white, then under this orange beam, and finally over the duct. We'll use the pseudo-calculator mode of the slide routine to place the top elbow at an elevation that will give us the exact clearance from the duct we specify. Before we start our real-world examples, let's do a little review of what constitutes a graded or sloped system. A graded system is any piping or plumbing systems whose axis is plus or minus 2.6%, but not 0% slope as shown here highlighted in green. An angled piping run is any pipings run whose grade is greater than 2.6%, but not vertical. To understand why the slide routine treats sloped pipe differently, let's look at some of the challenges that sloped systems present to computers. First, let's look at the fittings themselves. The fittings used in a sloped systems are made at true angles. That means a 90-degree fitting is 90 degrees, and a 45-degree fitting is 45 degrees. First, let's look at problems with sloped systems that have 90-degree fittings, which have their branches roll vertically, and how the slide routine will help solve this unique problem. If we look at an elevation view of this waste system, we see that the mains run has been properly sloped down as illustrated by the red dashed line, and the branch of the combination has been looked up vertically. This riser was connected to the branch using the branch's axis for alignment. Since the fitting angle is 90 degrees, the riser's angle will be perpendicular to the run as illustrated by the blue dashed line rather than plumb as desired and represented by the green solid line. What would happen if we aligned a slope system by simply aligning the UCS with the main and moving the fittings using the move command and a perpendicular O-snap? The result would be as shown here in this lav header. The vertical waste and vent pipes would be out of plumb with their associated fittings and misaligned as shown here circled in red. This would result in a substandard installation and likely require costly adjustments in the field. When the fittings are installed using the slide routine, the fittings will be placed correctly as we can see here. Now the fittings are perfectly plumb with each other and therefore the pipes are also plumb. This is the result we expected. Before we build the lav header assembly, let's look at this simple riser and see how the slide routine will not only properly position this elbow, but will also automatically supply us with some useful information about its slope and its branch's orientation. We'll also see the alignment options the slide routine will offer as we slide this elbow into position under the cleanout Y above. Practical uses for these options will be described in detail later in this video. Anytime the slide routine is used, it will try to figure out what type of alignment is most appropriate based on 3 parameters. The angle of the run, the fitting branch angle, in this case 90 degrees, and the branch's roll angle relative to the world coordinate system. In this case, the branch is rolled up vertically. I have removed the riser pipe and set the PD mode variable to 32 so the fitting nodes will display as a target rather than a point to more clearly get a look at what the slide routine does. When the slide routine detects that the slide axis is sloped, the branch angle is 90 degrees, and the branch is rolled vertical as shown here, it will automatically align the branch plumb to the alignment plane as represented by the white line. Let's use the slide command again to see what options were offered for fitting placement. We'll pick the 3 points to define the fitting, making sure to pick the focal point as a second point. Then we'll pick the center of the Y above for the point to align with. Let's zoom in on the command line. Here we can see that we are presented with three useful pieces of information: the slope of the slide axis in percent of grade, the branch roll in percent of grade. In this case, this would be infinity, so we have chosen to label it as vertical, and the current branch alignment type, in this case plumb to the alignment point. We can also see the two remaining options. In this case, the options are plumb to the focal point or perpendicular to the focal point. Let's zoom back out so we can see the elbow. Currently the elbow is aligned plumb with the Y above. If we enter an F on the command line, the elbow will align plumb to the focal point. Entering a B on the command line will again move the elbow's branch plumb with the Y above. Entering a P will move the elbow so the focal point is now perpendicular to the Y. At this point we can see that the alignment point options are circular, meaning that you can slide the fitting between any of the 3 points as many times as you need until you're satisfied with the position. This is true anytime the slide routine offers alignment options regardless of the fitting type. Let's enter a B on the command line to leave the face of the elbow's branch aligned plumb with the Y as it should be. We'll explore practical uses for the other options later in this video. Now that we have seen the options presented when the slide routine detects a sloped slide axis, let's see how it works in some real-world situations. Here's the lav header we saw in the beginning of this video. It incorporates a slope vent run that would normally be an additional layout obstacle, but will not be a factor when using the slide routine. Let's remove the pipe, couplings, and other fittings that will be installed using the slide routine. The end of the waste and vent runs shown here are the anchor points for this project and are installed at the proper elevation and grade. I have also pre-installed the sand tap tees at the positions shown on the architect's drawings and set their elevation as required. Let's use the slide routine to put both the waste and vent fittings in their proper positions. Let's zoom in and start with the sand tee on the vent system. Let's slide the first sand tee to align it with its associated sand tap tee. We'll pick the 3 points on the fitting, making sure that the focal point is the second point. Then pick any point on the center of the sand tap tee, and the sand tee slides to its proper position. If we look on the command line, we see that the slide routine tells us that the fitting was aligned plumb to the alignment point. This is where we want it, so we'll just right-click the mouse and leave the fitting where it is. Rather than installing the second tee with the piping dialog box, let's just copy the existing tee with the copy command and use the slide routine to adjust its position. As you can see here, just as in non-sloped systems, it doesn't matter which end of the slide axis is picked first. The slide routine will determine which direction the fitting will slide. We can also see in the command line that the fitting was aligned with the branch plumb to the alignment point, so we'll just click the right mouse button and exit the command. I've panned over and installed the elbow at the end of the vent run. Now we'll slide it on its axis just as we did with the sand tees. Once again, the routine has properly slid the elbow, so we can right-click the mouse and exit the command. I've returned to a wider view so we can move this first combination on the waste run. We'll do it like we did with the sand tees, only this time I'll restrict the O-snap for the focal point to a node, since the focal point on a combination is very close to the end of the fitting and could be mistaken for the end of the combination. For the last two combinations, rather than using the piping dialog box, we'll use the copy command like we did with the sand tees, only we'll use the multiple option to speed along the process. Since we know that by default the slide command will align the branch of the combination plumb to the sand tap tees, we can simply right-click the mouse to leave the fitting in a default position. Then right-click it again to restart the slide routine, then slide the next fitting into position. It's important to note that this entire assembly was completed using the slide routine exclusively, without the use of 3D center lines or calculations of any kind. All that's left is to install the couplings in the pipe and the lav header is finished. Let's look at our warehouse project and see an example where we may not want the slide routine to align the branch plumb to the alignment point. Here we have a portion of a fire protection system. We will be installing the nozzles shown here highlighted in red on the main and secondary pipe runs. As you can see from this elevation view, the main pipe run is sloped to match the slope of the roof. The secondary pipe run is perpendicular to the main and is level to match the roof in this direction. Let's switch to a split viewport and remove the joists, the main beams, and the columns. Now let's remove the nozzles with their couplings and restore them to their original position prior to using the slide routine. Let's start out by moving the nozzle on the secondary manifold. We'll correct its rotation after we slide the nozzle on the main manifold. Since the slide routine will decide which way to slide the nozzle, we can pick any point on the center of the pipe. Let's pick the center of the coupling in the elevation viewport. When I made the nozzle, I put a node where the center of the pipe it would attach to would be. This is the equivalent of a focal point, so we'll pick it when prompted to pick the focal point, and pick the end of the nozzle for the alignment point. Since the secondary manifold is not sloped, we can pick any point along the center line of the main manifold below, and the nozzle slides to align with it. Note that since the secondary manifold is not graded, there is no options to adjust its position on the command line. I have changed to a single viewport configuration for clarity. Now let's slide the nozzle on the sloped main manifold to align with the nozzle on the secondary manifold. Rather than zooming out to pick the first end of the pipe for the slide axis, we use the center of one of the grooves as the first point. Now we can easily pick the nozzle's focal point since it's co-located with the end of the pipe. When prompted, we'll pick the end of the nozzle for the alignment point. Now we'll want to pick the center of the secondary manifold as a point to align with, since we are not yet able to rotate the matching nozzle to the correct angle until this nozzle is in its proper position. If we look at the command line, we can see that the branch is aligned plumb to the alignment point. In this case, this is the center of the secondary manifold above. This is not what we want. If we left it where it is, the nozzle will be misaligned as shown here. To correct this, we want to enter P for perpendicular to the focal point on the command line. The nozzle now slides to the proper alignment point and is perpendicular to the center of the secondary manifold. When I installed the upper nozzle, I didn't have an accurate way to set its rotation angle, so I left it as is. Now that the bottom nozzle is in its final position, let's correct its rotation angle using the main manifold's nozzle as the aiming point. We'll use the 3D rotation tool on the Piping Extra toolbar to correct the angle. In slope pipe systems, this type of tune-up is often necessary when two or more points or fitting angles are initially unknown. To change the rotation angle to align with the opposite nozzle, we simply pick the center of the coupling on the secondary manifold for one end of the rotation axis, then pick the node of the nozzle for the other end of the rotation axis. Now we'll pick the end of the nozzle for the handle point. When prompted to pick a point or enter an angle, we'll pick the end of the nozzle on the primary manifold. Both nozzles align with each other perfectly. We'll simply install the pipe and couplings and we're finished. Now let's look at some non-90-degree fittings installed on a graded system. To do this, we'll look at our toilet room project. We will be working on the men's side for this exercise. As you can see, we will need to miss the structural members while maintaining the proper grade on the waste and vent runs. We will also be installing the plumbing for the 2 urinals and the 2 water closets shown here. Note that the handicap fixtures are at opposite ends of the piping run, which will require the elbow on the left looking down to be as close to the slab as possible. Like the lav header we saw previously, this system also incorporates a slope vent manifold. Let's switch to an isometric view that's behind the fixtures. We'll need to remove the walls, the beams and joists, the columns and the grid lines in order to get a clear view of what we will be doing. Let's zoom in. First, we will be aligning the Y and the sand T highlighted in yellow with the urinal highlighted in red. I have switched to a 2 viewport configuration showing an elevation view on the left using the hidden wireframe mode for a clearer picture of the urinal's outlet, and a conceptually shaded isometric view on the right. We'll be using the isometric view to pick the points and looking at the elevation view to clearly see the change in position of the fittings. The point selection for the Y is the same as in all other previous examples. Just as we saw in the first video, any non-90-degree fitting will slide to align its branch using the fitting angle. However, since the sliding axis is sloped, the slide routine will present us with a few options. Let's zoom in on the command line and see what these options are. We can see that the slide routine has slid the Y using the true fitting angle. The true fitting angle option will always compensate for three things: the branch angle, the slide axis slope, and the branch roll angle. We can also see that there are only options for plumb to the branch and plumb to the focal point. There are no perpendicular options available on slope pipe and non-90 degree fittings with vertical branches. Let's see what each of these options does. First, we'll enter a B on the command line and see that the branch is now plumb with the outlet of the urinal. Next, we'll enter an F on the command line and we see that the focal point is plumb with the outlet of the urinal. Uses for these options will be covered later in this video. For now, let's enter an A on the command line and slide the Y back to align its branch to the urinal's outlet and continue. I have placed the sand tap T on the Y we just slid into position. Now we need to slide it to align with the outlet of the urinal. Let's zoom in on the command line. We can see that the slide axis is sloped 104.3%, which is considered an angled slide axis. We can also see that the branch is rolled 0% or level. The next line tells us that the plumb, perpendicular, and level points are equal to each other and the level option is pre-selected. This means that the branch of the sand tap T is level with the urinal's outlet. In this unique case, toggling between the plumb and perpendicular points would not change the fitting's position. Therefore, other options are not offered. The only logical option in this case is the move additional distance option. This means that the slide routine has entered the pseudo-calculator mode, which will be discussed in detail later in this video. So for now, we'll press Enter twice to exit the command and leave the fitting level with the urinal's outlet. I've already installed the combination for the urinal, so we just need to slide it into position and we're ready to move on to installing and adjusting the toilet carriers. Since the combination's branch is rolled to the vertical position, by default it's aligned plumb to the urinal's outlet, so we'll press Enter to leave it where it is. I've already inserted the toilet carrier as a block. Now let's slide it into position. We'll pick the center of the end of the fitting to define the first point on the slide axis. As usual, we'll pick the focal point when prompted, but when we are prompted for the branch end, we find that the carrier has a different type of branch. It's not a circle with a single center like most other fittings, it's a slot for height adjustment. So in this case, we'll pick the center of the casting radius on top of the carrier. When the fitting slides into position, we can see on the command line that the branch is rolled up 95.9% or nearly a 45-degree angle. This is because the points we picked look to the slide routine as though we are trying to align a 90-degree fitting, such as this elbow shown here. Therefore, the slide routine is trying to align the top of the carrier slot with the toilet's outlet using the true fitting angle. However, this is not the alignment we want. What we want to do is align the carrier slot plumb with the toilet's outlet port. So we'll just enter an A on the command line and the carrier slides into the desired location. I should note that in this case the top of the slot of the carrier will align with the toilet's outlet. However, since the run is sloped, the bottom will be about a 32nd of an inch out of alignment. This is really of no concern and is what actually happens during installation in the field. Now that we have the fittings in place for the waste manifold, all we need to do is finish off the vent manifold. I have already installed the fittings using the copy command just like we did with the lav header we saw earlier in this video. Since all of the alignment points will be plumb to the branch, we can just slide the fittings on the vent run in rapid fashion. As we have seen when using the slide routine on graded pipe runs, we are presented with several options. It is not necessary to memorize which ones will be presented because the slide routine will only offer options that are appropriate for the points picked. A great amount of planning went into the default fitting placement in order to make the slide routine as intuitive as possible. The cyclical design of the slide routine's options allow you to toggle between each point until you are satisfied with the result. The options offered make the slide routine one of the most powerful and flexible fitting placement tools available. The slide routine will allow you to reposition objects in ways not possible with standard CAD move or 3D move commands. Once the fittings are in place, installing the pipe is as easy as drawing a line from one point to another. As we can see, placing fittings first, then piping between them is often much faster and more intuitive than using an auto router. Once the initial start points were established, this entire toilet room, as shown, was laid out entirely with the slide routine and without any other calculations. To see an example where we may want to align a fitting's focal point plumb to another point, Let's return to our warehouse project. Let's remove the perimeter beams and the columns for clarity. Here we will be positioning the Y on the roof drain system so its branch will miss the beam's flange as shown here. Let's remove the pipe and put the Y back at its starting point. We'll slide it as usual, but this time instead of picking the roof drain for alignment, we'll pick the lower end point of the beam's flange as shown in the elevation view on the right. If we look on the command line, we can see that by default the fitting is aligned with the beam flange using the true fitting angle. If we look at the isometric view on the left, we can see that the beam is interfering with the Y. This is obviously not the position where we want to leave it. If we enter a B on the command line, we can see that the Y moves so that the branch is plumb to the beam's flange. This is also not the position we want. Let's enter an F on the command line. Now we see that the focal point is plumb with the beam's flange and the branch of the Y is clear of the beam. Let's press the Enter key and leave the Y in this position. All we need to do is install the remaining fittings and the roof drain plumbing is complete. For this next demonstration, we'll use our parking structure project. Let's remove the upper structure that supports the ramp to get a look at the plumbing below. Here we'll install the plumbing for the rolling offset that connects the drains above to the riser next to this rather large column. Let's return the fittings to their original position and switch to an elevation view to start the demonstration. I place the riser highlighted in yellow in the position designated on the engineer's drawings. The position of the hanger, which is now highlighted in yellow, is aligned with the riser on the XY plane and its elevation is set as close to the beam above as possible. Since this location has the X, Y, and Z coordinates where the pipe will eventually be, making this rolling offset will be very simple. The drain pipe on the left, highlighted in yellow, was placed as high as possible to maximize headroom as required in the job spec. I've switched to a dual viewport configuration with a right side elevation view on the left viewport and an end elevation view on the right. I'll use the fitting rotate routine to rotate the 45-degree elbow to align with the hanger's center. The angle of this elbow will form the slide axis for the next elbow. For clarity, I've switched to a plan view in the left viewport and an elevation view in the right. I have pre-installed an elbow and rotated it so its outlet is aligned with the hanger. We'll pick the points on the new elbow for the slide axis and the alignment point. Next, we'll pick the center of the hanger for the point to align with, and the fitting slides into position. I should note that the elbow's horizontal branch has inherited the slope from the pipe above and will therefore be set at an elevation that is upslope from the selected hanger. I've switched to a single viewport that shows an elevation view. I have also pre-installed the third and final elbow below and looked its face down. Let's slide the fitting to align with the Y below. We'll select the elbow on its points as usual. This time we'll pick the top cup of the coupling on the Y for the point to align with. Initially the elbow will try to align on a 45-degree angle using the true fitting method. If we look at the command line, we can see that the slide routine has supplied us with the axis slope. This will confirm that the slope we inherited from the pipe above is correct. Now we just need to enter a B on the command line and the elbow's face aligns plumb with the branch of the Y. Let's move the Y up to match the end of the elbow. We'll need to be sure that we pick the bottom of the top cup of the coupling to get a tight joint with the elbow. At this point the fittings are all in proper alignment, but the hole offset is a bit too far from the beam above. Since the job spec calls for maximizing headroom, we'll need to slide the whole assembly. Let's select the two elbows, the couplings, and the pipe. This time we'll define the slide axis as the points between the two elbows and pick the face of the elbow that is facing up. Now let's pick the corner of the overhead structure for the point to align to. We can see that the elbows in the pipe have actually slid into the beam we were trying to avoid. This is because the elbow is now aligned with the corner of the beam that is farthest away from our viewpoint. Since the pipe run is 90 degrees to the beam, picking any point along the beam would work since we will be using the plumb to the focal point option. Let's enter a P on the command line and the fittings align underneath the beam as planned. Now we can just install the pipe and hangers, and the rolling offset is complete. Once again, the slide routine has allowed us to complete the rolling offset without the use of a calculator or calculations of any kind. Before we move on to our final comprehensive demonstration, let's explore the flat plan option and the true fitting option and see what they actually do. On the left, we have a plan view of a 2D drawing whose fittings were slid using the flat plan fitting angle. The flat plan fitting angle option is the way 2D drawings have always been done. On the right, we have a 3D model whose fittings were slid using the true fitting angle option. Let's see the differences. When the slide routine calculates the slide axis and the branch roll angle is within 2.6% slope, it will automatically align the fitting using the flat plan fitting angle option. This simply means that the branch end will align with the point to align with using the fitting's branch end as shown in the 2D model on the left, rather than the projected center line of that fitting as shown on the 3D model on the right. As you can see in this side-by-side comparison, the difference between the flat plan fitting angle versus the true fitting angle is about 5/10,000ths of an inch. This means that about a 1/16th of an inch of runout would occur for each 125 feet of run. This is of little concern in semi-flexible coupling systems such as groove pipe or no-hub soil pipe as shown here. So why are we offered an option in this case? In rigid systems such as stainless steel socket welded fittings, the true fitting angle may be required, especially when there are many slope fittings in close proximity to each other, since there is no wiggle room for adjustment once the fittings are welded together. Therefore, we have decided to let you decide which option best suits your needs. Before we look at the true fitting option, it's important to see why proper fitting rotation is critical when using the slide routine with the sloped slide axis. In the toilet room project, the first Y and combination had their branches rolled up vertically. Even though the urinal's outlets were not aligned with the plumb plane of the fittings, they aligned correctly. This is because the slide routine calculated the slope was standard and the branches vertical, and therefore inhibited the true fitting option. In the warehouse where we picked the end of the main manifold to align the first nozzle with, we could have picked any point along the plumb plane and it would have aligned correctly because the nozzle slide axis was level. However, in the parking garage we had to use the pipe hanger for a target to adjust the roll angle with. Since the branch's roll angle was much steeper than 2.6%, the slide routine defaulted to the true branch angle option. Let's look a little closer at the true fitting angle option and the effect branch roll angle has on it. On the left we see the Y that was placed using the flat plan fitting angle. On the right, the Y has been rolled up on a 45-degree angle to accommodate the elevation change of the branch, and the 8th bend was replaced with a 6th bend. Even though the dimensional relationship between the branch and the main is identical, the fitting geometry has changed substantially. Let's remove the pipe and move the elbow back to its original position. When I installed this 6th bend, I wasn't able to be exact with the branch's roll angle due to the compound angle of the Y's branch and the world coordinate system. Let's see what would happen if we leave the fitting as is and use the slide routine. Here we see the fitting has been slid to the exact position where its branch would intercept the plumb plane of the elbow. This happens because there are no other useful options possible. We will see why this is in the next exercise. For now, we can see this alignment is clearly unacceptable in this situation. The farther off the rotation angle is, the worse the alignment will be. Fittings like this 6th bend, whose run have been rolled on a compound angle relative to the world coordinate system, can be tricky to adjust. What we need to do is precisely rotate the fitting before we slide it into position. But how would we calculate this angle? The truth is, many CAD detailers would leave this as is and field cut and fit the connecting pipes. Fortunately, we don't have to make any calculations at all. We'll let the power of 3D CAD and a simple rotation tool do all the work for us. Let's look at the completed connection when it's done correctly. We can see here that the elbow's branch is perpendicular to the axis of the pipe as seen here. In this case, the branch is coincidentally parallel with the x-axis of the world coordinate system. Therefore, all we need to do is draw a line from the focal point of the 6th bend parallel to the x-axis using a standard polar tracking angle. Next, we'll use our rotation tool to rotate the fitting using the end of the new line as the alignment point. That's all there is to it. No calculations or field cut and fit piping required. Now let's slide the 6th bend into position. As you can see, when possible, fittings on a sloped or angled pipe run should have their rotation angle adjusted prior to using the slide routine. With a simple adjustment of the elbow's elevation using our Angle Z tool, we can install the couplings and the pipe and the offset is complete. This complex yet common rolling offset is a good example of how the proper use of 3D CAD can save time and money both during the layout process and in the field during installation. What if we have a situation where we have no known rotation angles and we need to use the slide routine to align a fitting? What do we do then? Let's look at this P-trap hookup. In this case, we want to keep the Y in place and slide the elbow. The rotation angle of the fittings are not defined by a specific branch angle like it was in the previous example. Rather, it is only governed by the fitting angle, the slide axis slope, and the elevation differences between the two pipe runs. In this case, we don't know the final rotation angle of either the Y or the elbow. Since the elbow will be slid on a sloped axis, we also don't know its final elevation. So where do we start? In this case, we know we want to leave the Y in its current position and only need to adjust its roll angle. The elbow is different. We need to adjust both its roll angle and its position, and thus its elevation. Let's start by sliding the elbow closer to its final position by using the Y's branch as the point to align with. Normally, we would rotate the elbow to align with the end of the Y's focal point, but for illustrative purposes, the elbow was slid using its current rotation angle. Let's install a pipe and see how the fitting alignment worked out. We can see that the pipe did not connect to the Y like we expected. Let's see why this happened. Switching to a plan view will give us a clearer explanation. Here we can see that the end of the pipe is aligned almost perfectly plumb to the end of the Y, which is similar to what we saw in the previous 6-bend example. Let's switch back to an isometric view to see what's happening. Here you can see the fitting and pipe where the slide routine placed them. Since the routine only asks for one point to align with, it assumes that the fitting is rotated to the correct angle. If the slide routine cannot find an exact point match, as in this case, it will default to one of only two logical points, which is nearly plumb to the alignment point, as seen here. The only other logical point is level with the point to align with, but this is only an option and never the default. We'll see how to take advantage of both of these options in the office project shown later in this video. Let's switch back to the original isometric view and tune up the rotation angles and the elbow's position. Since the elbow is very near its final elevation, we'll rotate its branch angle to align with the focal point of the Y. We use the focal point because we know it will never move regardless of the rotation angle of the branch. Let's tune up the Y's roll angle to match the new elevation of the elbow. Now we can re-slide the elbow to its final position. This may seem like a lot of adjustments, but in real time, the power of 3D CAD allowed us to complete this connection in less than 60 seconds. All this without one single calculation. Now the joints align perfectly, negating the need for field cutting and fitting of the pipes. Now that we have covered the fundamentals of the slide routine, let's look at our office project. We will be using the slide routine to install this waste run and its two branches as shown here in yellow. This project has several objects that the waste pipe runs must be routed over, under, and around, such as the supply and return ducting as well as the structural steel. This will let us use all of the options the slide routine has to offer and show its versatility all in one project. First we'll slide the Y in the main shown here highlighted in red to align with the pipes from the level above shown here highlighted in magenta. To do this we'll use the slide routine to position the fittings in this vertical offset shown here highlighted in magenta. Finally we'll use the slide routine to place the fittings for the rolling offset shown here also highlighted in magenta. To do this we'll use the level to object option along with the pseudo calculator function which we haven't yet seen. I switched to a dual viewport configuration in order to get a better view of the plumbing run. Since we're working above the ceiling, we'll remove the architectural entities for clarity. Let's remove the pipe and move the fittings back to their original positions. Sliding the Y, reducer, and 45-degree elbow is simple. We just select the object to slide, pick the 3 points to define the object, then pick the point to align with. In this case, it could be either the riser or the elbow. Now the Y, reducer, and 45-degree elbow slide into position. If we look at the command line, we can see that the branch of the Y was aligned with the riser using the flat plan angle option, which is what we want. We can also see that the larger main was sloped at 1.5%, or just over 1/8 of an inch to the foot, like we would expect on a live job. We can also see that the smaller diameter branch is sloped at 2.1%, or 1/4 of an inch to the foot. The difference in the pipe grades is due to the pipe diameter and was dictated by the mechanical engineer's design criteria. The differential slope combination will automatically be compensated for by the slide routine. Let's press enter and leave the fittings where they are. If we were to connect the Y to the elbow in the position it is now, we can see that the pipe shown here highlighted in blue would collide with the supply and return duct shown here highlighted in green. So we'll need to adjust the elevation of the elbow. As we saw in the first video, the slide routine will slide entities on the Z-axis but does not offer any further elevation adjustments once the fitting is in position. So we'll have to use another routine called the angle Z routine. Since this video is intended to provide in-depth instruction for the slide routine, instructions for the angle Z routine will be limited since it's covered in depth in a separate video. The angle Z routine uses MetQ's auto slope feature for grade calculations, so we'll need to turn it on before we adjust the elevation of the elbow. The auto slope control dialog box is accessed both inside the piping command as well as with the settings buttons of the MetQ piping extra button bar. We'll find it here under the gear flyout button. When we open the dialog box, we see that the data fields are grayed out. Let's check the auto slope checkbox and turn on auto slope. Now we can see that the fields appear in black and are editable. We see that the slope is set to 1/48, which equates to 1/4 inch to the foot, since there are 48 quarters and 12 inches. As far as the angle Z routine is concerned, the up or down radio buttons are not referenced, so we'll leave them as they are and click OK to save the settings and exit. I've zoomed in to get a better view of the elbow and the elevation adjustment we'll be making to it. You can see how far inside of the duct the pipe is at this point. Let's select the elbow and adjust its elevation. When prompted for the alignment point, we'll pick the lower quadrant of the elbow, since this is the point that will match the bottom of the new pipe. When prompted for the point to align with, we'll pick the top corner of the duct as near to the point as we can where the pipe will cross it. The distance from this point to the quadrant of the elbow will be used by the angle Z routine to calculate the new elevation of the elbow. Now that we have picked the points, let's zoom in on the command line. We can see that the angle Z routine has detected that auto slope is on and presents us with a few options. The plus sign to move up, the minus sign to move down, and an A to enter an angle. Since we want the elbow to be higher than the duct, we'll press the plus key and the elbow will move so the lower quadrant of the elbow will be graded up from the point on the upper corner of the duct that we just picked at 1/4 of an inch to the foot. If we were to leave this elbow where it is, we would be guaranteed that the pipe we'll be installing would just touch the supply duct's top edge. So we'll need to make some further adjustments. If we look at the command line, we can see that the angle Z routine has supplied us with some useful information and entered the pseudo calculator mode. The information it provides us with is the angle from the lower quadrant of the elbow to the top corner of the duct, the elevation of the lower quadrant of the elbow to the top of the duct, and the grade in percent from the elbow to the duct. In this case, it's 2.0833% as per the auto slope settings. This information is always presented in the format set in your CAD engine's units options. Remember, the distance shown here is the distance the elbow is above the duct, not the elevation of the pipe from the duct at the selected point. That dimension is currently 0 inches. The bottom line of the command line prompts us for an additional distance to move the objects. If we want to move the elbow down, we would enter negative numbers. However, in this case, we want to move the elbow up, so we'll enter positive numbers. In the pseudo-calculator mode, the angle Z routine will change the elevation of the objects accordingly and keep a running total of the distances entered. This feature eliminates the need for a dimensional calculator. First, we need to move the elbow up 2 inches to clear the insulation on the duct, so we enter 2 for 2 inches on the command line. Now we see that the angle Z routine has recalculated the elbow's current elevation, and it is now 2 inches higher than it was, or 7 3/16 inches above the duct. Since we are trying to keep the plumbing as low as possible, we'll enter 1 1/2 inches for the additional amount we want to clear the duct insulation by. Now the elbow is 8 11/16 of an inch above the point we picked on the duct as seen here on the command line. We'll press enter to exit the angle Z routine and leave the elbow at its new elevation. Let's switch views to get a better look at the 45-degree elbow we'll be sliding into position. I have pre-installed the elbow with its run graded down 2% and its branch looking straight down vertically. We'll pick the points on the elbow as usual, but when prompted for the point to align with, we need to pick the corner of the duct near the point where the new pipe will cross it. The actual slide axis is shown here as an animated dashed line. Ideally, this point should be identical to the point we supplied to the angle Z routine, but since we'll be using the plumb to the focal point option, an exact point match is not necessary. Since the branch is looking straight down, by default the slide routine will initially try to align the elbow's branch with the point on the corner of the duct we just picked. This is not what we want, so we'll type F for plumb to the focal point. This will ensure that the fitting will clear the duct. Now we just need to press enter to exit the command and the elbow has been properly placed. I switched to a single viewport configuration to slide the final elbow in this vertical offset. We need to slide the elbow highlighted here in yellow to align with the elbow we just slid into position, shown here also highlighted in yellow. Initially the elbow will slide to align its branch with the elbow near the top of the duct, which is what we want. Before we press enter to exit the command, we should note that the command line shows the slope of the run. This information can be used to double check the Y's rotation angle prior to installing the pipe. Now we simply install the pipe and couplings and this vertical offset is complete. For the final demonstration of this video, we'll look at the other branch of this waste system. Initially I tried to route the pipe as shown in the mechanical engineer's drawings, however we can see that the pipe ran into the web of the beam and through some of the ducting. This problem is common with many pipe auto routers since most of them have no awareness of obstacles. To solve this somewhat complex problem, we'll use the slide routine and its own pseudo calculator to make fast work of the often dreaded rolling offset. To solve this problem, we'll run the pipe under the beam and roll the elbows up to clear the top of the duct as shown here. I originally used a 45-degree elbow and a 22.5-degree elbow to solve this problem since the slide routine does not depend on equal angle fittings to make an offset. The offset shown here would be impossible to figure out using standard tables, piping calculators, or auto routers since they are normally restricted to equal angle fittings. However, after I finished installing the pipe, I found I didn't have enough clearance on the duct, so I switched to the more common double 45-degree elbow offset shown here. We'll switch to a flat plan view where you can see I've removed the pipe and fittings. The first elbow has already been reinstalled and rotated to the proper angle. This elbow must be slid far enough to clear the flange of the beam and still leave enough travel for the offset without hitting the duct. When I pick the point to align with, I can simply pick a point on the XY plane that will clear the flange of the beam. Since the branch is rolled up steeper than 2.6%, the slide routine will try and align it using the true fitting angle, which will actually end up plumb to the point picked, like we saw in the 6-bend and P-trap examples earlier in this video. Let's switch back to a split viewport with an isometric view on the left and an elevation view on the right. I've used the clipping option in the right viewport to clip off the perimeter beam and the S-duct that obstructed our view of the pipe and relevant duct. I have also installed the elbow we'll be sliding and rotated it to the proper angle. We'll select the elbow as usual and use the nearest O-snap to pick the top of the duct. Due to the slide axis angle, the slide routine will automatically try to align the elbow plumb with the point we picked on the corner of the duct using the true fitting angle method. This is just like we saw earlier in the P-trap example. This time we want to use the level with alignment option, so we'll enter an L on the command line, and the center of the elbow aligns with the top of the duct. If we look at the command line, we see that the slide routine has informed us that the center of the elbow is level with the top of the duct, and the slide routine has entered the pseudo calculator mode. Anytime the slide routine prompts us for an additional distance to move, this is our signal that we are in the pseudo calculator mode. The distance is entered in the pseudo calculator mode preceded by the minus sign will move the elbow down relative to its current position, while distance is entered without a sign will move the elbow up from its current position. It is important to note that even though the elbow is moving on the X, Y, and Z axes simultaneously, The distances entered on the command line are the changes we want to make in the elevation only. The slide routine will do all of the calculations necessary to keep the elbow in line with the slide axis. This means that anytime we're going to use the level with the alignment point option, we can pick any point in the drawing that has the elevation we want the center of the fitting to align with. If we wanted to reference a beam or pipe on the other side of the building, we could simply pick that point to use its elevation as a reference. The slide routine will slide the fitting along the slide axis until the fitting center is at the selected elevation. But for this example, we use the duct as shown. Let's enter a few distances and see what happens. When we enter a 1 for 1 inch, the elbow moves up 1 inch from its current position. XY movement is done automatically by the slide routine. When we enter a 2, the elbow moves up 2 additional inches for a total of 3 inches above the duct. Entering a 3 will move the elbow up 3 additional inches for a total of 6 inches above the duct. Entering a negative 1/2 will move the elbow down 1/2 inch to bring the total distance above the duct to 5.5 inches. If we enter a 0, the slide routine will always move the object level to the point to align with, in this case the top of the duct, regardless of their current elevation. So let's do that now and bring the elbow's center back level with the top of the duct. If we enter numbers preceded by a minus sign, the elbow will move below the duct, and the pseudo calculator will show this on the command line. This means that even if you're not viewing your model from an elevation view, you still know how far above or below your objects are relative to the point you're aligning with. Let's enter a 0 on the command line and slide the elbow center level with the top of the duct. Now we can slide the elbow up to give it proper clearance with the duct. Since we had to pick the center of the elbow's branch for an alignment point, we'll enter 2¼ inches for the outside radius of a 4-inch waste pipe. At this point, the bottom of the connecting pipe would just touch the top of the duct, so we'll enter 2 inches for a duct installation and another 1.5 inches for additional clearance. This brings the total distance from the center line of the elbow to the top of the duct to 5¾ inch. As you can see, the pseudo calculator will accept any dimension format that your CAD engine recognizes. Let's bring the text screen up and look at the dimensions we entered. The column on the right shows the dimensions as we enter them, which makes it easy to recheck our entries for accuracy. Let's start with the second 0 in this column. This is where we leveled the elbow with the top of the duct. We see the 2¼ inches for the pipe radius, the 2 inches for the duct installation, and the 1.5 inches for the cushion. This totals 5¾ inch as shown here. I've switched to a dual viewport configuration in order to finish the office project. All we need to do is slide the original 45-degree elbow to align with the new offset and adjust the elevation. Since the 45-degree elbow is already sloped, all we need to do is pick the points as usual, and it slides into position using the flat plan fitting angle option. This is what we want, so we'll just press enter to exit. We need to make one more elevation adjustment on these 2 elbows, since we don't know if they are on the correct grade relative to the elbow used in the offset. We'll just use the angle Z routine and the auto slope settings to adjust the elevation of the elbow on the riser and the 45-degree elbow we just slid into position. Now all we need to do is install the couplings and the pipe, and the rolling offset is complete. This rolling offset and collision avoidance was done with just 4 mouse picks per fitting and entering the vertical clearances we needed. If we had enough clearance, we could have made this offset using fittings with different angles, such as the 8th bend and the 16th bend we saw earlier. This is a feature not supported by most auto routers or piping calculators. The slide routine makes using any combination of geometrically compatible fittings to make an offset a possibility. All you need to do is rotate the fittings to the correct angles, and the slide routine will do the rest. Whether you're a piping detailer using MECQ for system design and installation, or plumbing detailer using MECQ for system layout, coordination, and as-built drawings, you'll find the slide tool will quickly become one of your favorite software tools. Finally, the object-oriented power of 3D CAD has been made accessible using this new tool. Now you can spend more time optimizing your design and less time trying to figure out how to place 3D objects where you want them. That's good for you, good for your clients, and most of all, good for the bottom line. The slide tool was developed by Real World CAD as a robust tool for the mechanical detailing industry. At Real World CAD, we believe that you shouldn't need a degree in software engineering to produce CAD drawings that are accurate, legible, and completed on time. The slide tool is only available in the MECQ software suite and AviCAD, which is now available from cadavenue.com.